So, we had been looking at the application of derivatives. The key idea which we have been emphasizing is that derivatives the derivative at a given point actually linearizes the function. That is, you can approximate the function values near say x f x or near x, the point x where you are computing the derivative, by the value of the tangent line drawn at x f x on the graph, and in fact the tangent line has to be expressed through derivatives. Today we are going to talk about how to solve f x is equal to 0. So, the question is, find x hat in R such that f of x hat equal to 0, where f is a function from R to R. Now, why such a study is required? So, what we are going to do today, you are taking the first steps into a subject called numerical analysis. A very important branch of mathematics required everywhere, engineering, business, even in sciences. You might ask, oh, what is there in solving an equation? I have been solving equations for such a long time. In school, I have been solving equations. What was I doing in school? I was solving equations. Now, I would turn around and say that I might just give you an equation would be very difficult to solve. For example, you are aware that you can solve quadratic equations of the form ax square plus bx plus c. You can use the Brahmagupta's formula or the standard quadratic equation formulas, but there are several methods. One of them is by a famous Indian mathematician called Brahmagupta, who was a court mathematician in Ujjain. So, here of course we should have a not equal to 0. So, this is a polynomial equation, an algebraic equation which you know how to solve. There are other equations called cubic equations. This is called a cubic equation in the standard form, but it is not so easy to solve it like this one, the quadratic equation. And the idea of complex numbers, which you have already some information about in high school, the numbers of the form a plus ib, they also arise while trying to solve this equation. Not by, usually we say there was a desire to solve an equation of the form x square equal to minus 1. Of course, everybody knows if I put a real number x and square it, it cannot be a negative number. So, it came while trying to solve this. There is a famous solution called Cardano's solution or Tartaglia's solution. Italians are pretty good in all these things, by the way. Of course, you can talk about a algebraic equation or a polynomial equation whose highest power of x is 4. This is called a quadratic equation, this is a cubic equation, 4th degree equation, and that is it. Once the 5th degree equation comes and above, it becomes impossible to solve it. That is the famous theory of Galois, a famous French mathematician who died only at the age of 21 in a very stupid duel, and he did a large part of his work just before he was dead. So, Galois said that here what is happening, to express the solution I am using square root, here I will be using cube root. In the 4th degree polynomial I will use the 4th root. But what Galois said, that once you have a polynomial equation of degree 5 and above, there is no way you can solve it through radicals. Radicals means taking the root of that particular power. That is, you can't solve it by you taking 5th root, or a 6th degree equation you can't solve it by taking the 6th root. So then what am I supposed to do? That is the big question remains. So does that mean that I don't need to solve equations of the form fx equal to 0, where x could have higher power higher than 4? For example, if I simply ask you to minimize fx equal to x6 plus x4 plus 1, if I ask you to do that, you immediately know what to do. This is a differentiable function, and so your first step would be to check out what is this, and this immediately will give you 6x5 plus 4x cube equal to 0. So here you would immediately have x cube 6 x square plus 4 equal to 0. So either you have x cube equal to 0 or this equal to 0. So you will be able to solve it. Now suppose I had much more higher degrees, right? Suppose I put in more other degrees. For example, I take x8 or x9 or something like that, and your first degree, if I put, for example, if I put x here additionally instead of just plus, I put x here. So then here what you will have, this equation will become 6x5 plus 4x cube plus 1 equal to 0, and that is it, you are done, you are finished. You have no way to solve it just by factoring or getting things like this. So once you have one constant here, you are done. This is a 5th degree equation, 5th degree polynomial equation, and you cannot solve it by radicals. How would rather you would solve this equation? Then you have to resort to what is called Newton's method. Let us understand that Newton did his method earlier, much earlier. He was just trying to apply the notion of the derivative, and they were doing things for trigonometric functions and all those things. The Newton's method become very important when they realize that if you want to have degrees above 5, if you want to solve polynomial equations of this form, 5th degree and above, then you really have to resort to this Newton's technique. So what is Newton's technique? So let us look at the geometrical idea behind Newton's method. This idea, I want to emphasize again, rests on the fact that if I take points very near a given point, say x naught, then I can actually replace the function value by the tangent at x naught f x naught. Essentially it says, it builds on that particular idea that very near x naught I can actually approximate the function values in terms of the values on the tangent line. Though we talk about exact sciences, our natural sciences are called exact sciences, but I would let me tell you that a lot of important things in exact sciences are just done by approximation methods. So what is the idea behind? Of course, you can ask whether there is a solution or not of this equation. That is the first question one should mathematically ask, but let us start with this very naive assumption that it has a solution. So maybe this is the solution and this is the line. So this is my fx, this is the graph of fx. This is the graph of fx. Now what is the key idea? So, here is the solution. I really do not know it. Here I can see it because I have just drawn the graph purposefully. I do not know what the solution is, but what I want to now do is take any point as my starting point and then progressively move towards the solution. So, let me take this starting point as x0 on the graph x0 fx0. So, this is my starting point. So, this is my solution x hat and this is my starting point x naught. So, what I do at x naught fx naught, I draw the tangent and see at what point the tangent cuts the x axis. That point I rename as x1. So, now what is the corresponding point on the graph of the line? It is this one. So, this is now x1 fx1. So, now I draw a tangent through x1 fx1 and call this point as x2. You see I have come quite near the solution and basically take the tangent at x1 fx1 and then see where it cuts the x axis, and that is where does this tangent line become 0, and that is the point x2. And similarly you can do for the point which is x2 fx2, this point which is x2 fx2. I do not want to draw it, it will look very clumsy, and if you draw it, if you draw a tangent line, you are very near the solution, which this point is x3. So, what we have generated is a sequence of points which are moving towards x. It looks very simple, but let me tell you that this has its this has some more ideas involved in it. So, we have never spoken about what is the meaning of a sequence of real numbers, but we are telling that here we have generated a sequence of real numbers if we apply this methodology. So, we will give you a very brief idea of what is a sequence and what is the meaning that this sequence is moving towards a given point. And that would then help us build the Newton's method. So, sequence, you understand, are, so in general, though we have started with x0, x1, x2, xn, maybe the starting point could be x1, does not matter. Sequence, if you take a function from the natural number n to r, this is called a sequence. That is, you take every number 1, that is f1, you list all the numbers f2, f3 and so on. So, this one we call x1, this one we call x2, this one we call x3. In our case, we have defined what is called a sequence. It is infinite, it is countable but infinite. You have already spoken about countability and uncountability in a detailed way. So, you understand that we are producing a countable set. So, sequence is a countable set, and here what we have done, we have, for us, we have devised a mapping like this. This is also a sequence, does not matter whether you take this or this essentially. So, in this case we would have x0 and f of 0 and x1, then x2, then x3. For example, the sequence that I have generated here, 0th point, first point, second point, third point. And of course, for example, I will give you an example of a simple sequence, fx is equal to 1 by n. So, maybe I can't start with 0, obviously it does not make sense. In this case I start with n equal to 1, and it will have 1 half, 1/3, 1/4 and so on and so on. But observe, keep an observation on this sequence, that these values are constantly going down and going down towards 0. In such a case, we say that 1 by n converges to 0. This is a discretized version of the fact that 1 by x converges to 0 if x goes to infinity and each x is positive. So, it is nothing but some sort of a discretization of the graph or of the function 1 by x on the positive upon the positive part of the x axis. So, this is so limit of 1 by n we would say as n becomes larger and larger, which we indicate by the sign n tends to infinity, is equal to 0. Now, that is what is meaning that the sequence is approaching a point. That is the meaning that the sequence is approaching here. That does not mean that sequence will be only here. Sequence, for example, if I take it from x3, I could have a point which may just cut across it may just come this side, and again it will go back to this side. So, it can come in both sides of x hat. It is not just that it has to be in one side of x hat. So, this is a very brief idea what is the meaning of convergence. So, now I will start explaining to you what is essentially Newton's method. So, Newton's method is essentially an iterative technique. So, what is iteration technique? So, there is some sort of a black box which is an operator where we do some operation on a given point. So, you put in some x0 and out comes x1, and now you feed back that x1 into the same mechanism and out comes x2, which when you again feed back x2 into the black box, out comes x3 and so on. So, this is called the iteration technique, and by doing so you generate this sequence x0, x1, x2 and so on. How do we do in the Newton's case? So, let us look at this first starting point. So, here is my graph and here is my starting point. So, here is my x hat and here is my starting point. So, here is x0. So, as I told you, I will take the point x0 fx0 and draw the graph or draw the tangent. So, what is the equation of the tangent? So, take any xy on the x fx on the tangent, so xy. So, the tangent line is given as y is equal to, so very simple, we have to find the slope. So, slope is y minus fx0 by x minus x0, and that is nothing but what is the slope of the tangent? Slope of the tangent passing through x0 fx0 is nothing but the derivative at x0. So, y is equal to fx0 plus f dash x0 into x minus x0. So, our first attempt to get x1, so x1 is my solution to the fact that this must be equal to 0. That is, I want to ask a question, what is that x for which the tangent line cuts the x axis? So, if x1 is that point, then in that case f of x0 plus f dash x0 x1 minus x0 is 0. Now, suppose you can see from this. So, for example, theta, this tan of theta is not 0. So, f dash x0 is not 0. So, I can write x1 minus x0 is equal to minus f of x0, bringing the fx0 to the other side and dividing it by f dash x0, because f dash x0 is not equal to 0 from the diagram, and this simply means that x1 is equal to x0 minus f of x0 by f dash x0. So my mechanism is like this. So my general mechanism is like this. So if I want to now find, I have found x1, so I know what is x1 fx1 on the thing, and then I draw a tangent through x1 fx1, and I want to find what is x2. You know that you have to just now replace x1 with x2, x0 with x1. So x2 would be equal to x1, assuming again that, look at this theta 1, where you do not have, the angle is not horizontal, that it will become 0, the derivative. The derivative cannot be 0, the tan of theta cannot be 0. So it is x1 minus, so I am just replacing x1 with x0 with x1, x1 with x2, f of x1 minus f dash x1. So this is the general, this is the scheme. So this is the feedback mechanism. So I am just replacing. So if I want x3, I will put it at x3 is equal to x2 minus fx1 by f dash x2. But this allows me to write a very general scheme for getting the Newton's method, computing something through the Newton's method. So in general, if I am at xn, I want to know what is my xn plus 1, and the general scheme is that xn plus 1 is xn minus f of xn divided by f dash xn, and of course we know that f dash of xn must be non-zero. Now this is my Newtonian scheme, but you might ask me, okay, you will just keep on doing it, when will you stop? The real stopping thing would be when xn would be near x hat, right, when xn would be near x hat. So what you have to do, when do you stop? So you will stop when xn would become equal to xn plus 1. So you have actually reached this point, because when you reach this point, if you draw a tangent, it will not cut the x axis again, you will reach x hat, and that is the reason you stop. So this is the time when you stop, but who knows, will you ever reach this? So you might take infinite, countably infinite steps to reach this, that is the meaning of something going towards a limit, or when n goes to infinity. So what will you do there? That is the question, how will you stop? When I was in the basic undergraduate, doing my undergraduate studies, we were told that, okay, you just keep on looking at the values of x that you generate, and once you see the values are stabilizing, the decimal part is stabilizing, stop it. That is not really a proper answer, not a proper mathematical answer. You really have to find f of x hat equal to 0. So the way things would be done in an algorithm is to fix epsilon greater than 0, and this is called and epsilon is called the tolerance limit. Epsilon is called the tolerance limit. Now, in practice, I might, or in most cases, I would never reach x hat. So what I am supposed to do? I am supposed to be happy with some xk, k greater than 0, or it is n greater than 0, or n element of n rather, such that f of xn is strictly less than epsilon. If my functional value is less than epsilon, the absolute value of the functional value is less than epsilon. So the function value could be the n could be here or here, very near that point basically. Then it is alright for me, and that is where I stop. So when you do a Newton step, so every time you have to calculate xn and you calculate fxn, and you see whether mod of fxn is less than your tolerance. When you have reached the tolerance, you stop. So this is what in the modern day language would be called the stopping criteria. And this is what you need to follow. Xn, see, you understand very well. For example, if I want to find the square root of 2, I cannot really go on finding, I would never reach a irrational number, because I will try to generate sequences which are rational, because if these are integer numbers and they could be just rational numbers, and might be that I will never reach that root 2 point, it is impossible. So what I would do, I would stop somewhere and take an approximation, a rational approximation as my happy solution, because what I would ultimately get here is a rational approximation of, at every time I am getting some xn plus 1 which I represent through a decimal, which may not always be rational of course, but I will be happy to just have a rational approximation of actual solution. So that would suffice for me. So an approximate, this is essentially called, if you take an xn like this coming out and having this solution, then this is called an approximate solution, right. If f of xn is 0, anyway it will satisfy this whatever be your epsilon. So let me now, once it is there, let me now give an example of how your things can work. But there is a little catch. Before I give the example, let me tell you, you cannot, the Newton method works very fast. Newton methods work extremely fast. Now means you start with an x naught and you just reach immediately to the solution very fast in few iterations. But there is an issue, you have to be clever enough to choose your solution x naught. Sometimes if you are very far off from the original solution, you might not converge to the solution and might go in some other direction. So from a more point of view of more advanced mathematics, in the study of the theory of equations, one of the solution of equations, it has been told very clearly, it has been shown that if there is a small radius or small delta around x hat, so if you take x naught to be a point within that delta neighborhood, then you will converge very fast. If not, we do not know. Now you might say, oh, what is the use, how do I know a delta around x hat, I do not know my x hat. So here again your guess and test. So this is what the art of actually computing, that you start with an x naught, and if you see that you are not converging after a long time, then you understand something else has happened, change your x naught. Another way, we now with mathematical software, you can graph the function and then try to guess where you want to start. Sometimes from the graph you might get an idea of the solution, sometimes not, but some fair solution you can see where, in which part of the graph is very near 0, and then you can start something nearby. So this is a thing that one has to do when one really goes for an implementation, but mathematically, if you assume that there is a solution, then we say that there is a solution x, there is a delta greater than 0, and if you take the delta neighborhood around x hat, and then for any x naught in that x hat, we will very fast go and hit the solution. It will not hit the solution, means we will reach the solution. For example, if I want to say solve, now this is the equation, fx is equal to x square minus 2. So what I am trying to find, what is x? X is the square root of 2. So how do I compute this? By this methodology. Here, so my technique would be xn plus 1, so my Newton iteration scheme is xn plus 1 minus xn minus f of xn, which is xn square minus 2 and divided by 2xn. Okay. So this is xn minus xn square by 2xn minus 2 by 2xn. So, I can write this as xn minus xn square cancels with xn. So, xn by 2 minus 1 by xn. So, what I have here so if I look at it very carefully, this is what I have. So, it is xn minus xn by 2 minus 1 by xn. Of course, you can say half of xn minus 1 by xn, or you can say now xn plus 1. So, not minus 1 by xn, it will be plus 1 by xn, plus 1 by xn. So, what do I get from here? I can write this as half of xn square plus xn square plus 2 by xn. So, this is the scheme. So, now you do not even have to calculate the derivative or anything, so you just have to know what is xn, start with some x naught and just put it put this formula, you will get xn plus 1. So, you can do it for many functions. This I am sure or TAs would give some homework in this. For example, you can take, for example, there is a problem from Thomas's calculus, x cube minus x minus, this is a very standard problem given in many classes. I also did that when I was a graduate student, undergrad student. So, how will you handle this situation? So, you will start with some point and then start moving in, and you know here you have to find f dash x is equal to 3x square minus 1. So, your xn plus 1 in this case would become xn minus x cube n minus xn minus 1 by 3 xn square minus 1. Of course, I would also ask you to try to find fx equal to x square minus 3. So, that is the square root of 3. So, here you have a brief idea of how actual numerical computation goes. So, this is your first step into numerical computation, and I am pretty, I have just tried to give you a very basic idea of how things are there. I hope I have done my job. I hope that you have you've got a pretty decent idea of how to handle it. But when you compute, because here we can't go on computing and showing you things. If you compute, please understand that this is the way you should actually stop your algorithm, not any other way, not by looking, oh guys come on, it looks it is getting stabilized. No, that is not the way, that is not the way. You really have to check whether your solution is really near 0, the function value is really near 0. Because we can't reach the 0, we are happy with this sort of approximation, this sort of that okay, if the function value is very small, the absolute function value, that will do. Okay, thank you very much. We will speak about optimization problems in our next class and hope that you are enjoying the course.